Hello, everybody. Welcome back to the last afternoon for the conference, and we save the best for last. So if you survive until now, you're in for a treat. So the first speaker in the afternoon is Andrew Lo. Professor Lo is well known in both the economics and finance communities. He has made significant contributions to many different areas. He could have spoken in any of the days of the conference here, but he chose to speak on the day where we are reflecting on foundations because he's going to talk about evolutionary foundations of behavioral finance.
So I'd like to start by thanking Matthias Gressle and the other organizers for this conference, as well as Fields and INET, and of course all of you for staying till the bitter end. I know that it's been several intense days of various different topics, and I'm delighted to be here on the last day, particularly in the session on foundations, because one of the things that I've been struggling with for the last several years is how to reconcile the foundations of neoclassical economics and finance, the efficient markets hypothesis, with all of the recent evidence from the behavioralists about the kind of biases and psychological disorders that we all seem to suffer from. And so what I'm going to talk about in the next 15 or 20 minutes, just a couple of examples of how my co-authors, Tom Brennan and Rushin Zhang, and I have been trying to reconcile these two very disparate perspectives. And I think it's really part of this new economic thinking that INET has been trying to encourage that has given us the opportunity as well as the courage to take some of these views and start describing them to our colleagues in economics and finance. So let me begin by pointing out something that I think all of you know, which is that economists are incredibly narrow in their perspective on modeling human behavior. Now, you might think of that, particularly if you're outside of economics, you might think of that as a disadvantage. But I could tell you that economists are quite proud of that fact. We are proud of the fact that we are consistent in our perspectives on how people ought to behave. And that consistency has come about from the theory of economic behavior known as expected utility theory. This is an idea that was pioneered in the 1930s and 40s by a combination of von Neumann and Morgenstern and Paul Samuelson. The idea being that individuals behave in a way to maximize expected utility, where utility is some concave function and the expectation can be computed with respect to the objective distribution underlying the uncertainty in this particular framework. Now, what's that? Should, that's right. But economists have gone from should to does, and it was quite a leap of faith. The fact is that this theory is the only theory you will learn in graduate school. If you're a PhD student in economics or finance, from the very beginning till the very end, this is the only mode of behavior that is hypothesized, and it underlies virtually every single economic model that you will ever come across, including Black-Scholes, CAPM, arbitrage pricing theory. All of these ideas really take as their beginning expected utility. And over the course of the last few decades, psychologists, behavioral economists have documented a variety of departures from this kind of paradigm. And these are all the behavioral anomalies that you might come up with if you were to read now the modern literature on behavioral economics. One summer, I spent the entire summer reading through that literature, and by the end of the summer, I was convinced that the human animal was the stupidest creature on earth, because we all suffer from these biases: probability matching, loss aversion, anchoring, framing, overconfidence, overreaction, and so on. And I want to give you an example of just one of these biases, and then show you the kind of evolutionary explanations that my co-authors and I have come up with to try to understand where these things come from. And that's probability matching. So probability matching goes like this. Suppose that we're going to play a very simple game, a coin tossing game, where I have a coin, that it's my coin, and so I toss it over the course of many trials, and you try to guess at each trial what the outcome is. And if you guess correctly, then I'll pay you $1. But if you guess incorrectly, then you pay me $1. Okay? So a very simple game where we do this over an extended period of time. And I'll tell you right now that the coin is biased. But I'm not going to tell you what the bias is. It's my coin. I take it out of my pocket and I toss it. And after a while, you realize, after repeated trials of the same coin, you realize that heads comes up 3 times more frequently than tails. So 75% heads, 25% tails. What's the optimal strategy? What do you do at that point? Always guess heads. Of course, that's the optimal strategy. That's the profit maximizing strategy. Always guess heads, right? When you run this experiment, it turns out that people don't do this. What they do instead is something far more puzzling. They actually randomize their guesses. But here's the odd thing. The odd thing is that they actually randomize with the frequency that actually matches the frequency of heads and tails. They guess heads 75% of the time, and they guess tails 25% of the time. Now, they don't know the bias. It's just that after 20, 30, 40 trials, somehow they start matching. And if in the midst of this game you switch coins surreptitiously to a 60-40 bias, then you wait another 20 or 30 trials, what happens? They actually change the frequency to 60-40. They match probabilities. And what's even more fascinating is that this behavior is actually found in many other species. Ants, fish, pigeon, monkeys. Virtually any creature that can choose between A versus B, you can set up an experiment where actually they will engage in probability matching. Now, you might think this is a very silly example, but I'll give you a context where it actually took on a very serious overtone. And this I heard from Steve Ross, who told me he heard it from Amos Tversky, the Stanford psychologist who died quite a while ago. So I have no way of verifying it, but you can ask Steve Ross, and he'll verify that he heard it from Tversky. During World War I, the United States ran a number of bombing missions over Germany. And before the pilots got onto the bombers, they had to make a decision. They had to choose whether or not they wanted to wear a parachute or a flak jacket. Now, these two devices were designed to protect them from certain potential threats. A parachute was going to be useful if you got shot down by anti-aircraft missiles. But a flak jacket was meant to protect you in case you were hit with flak from mortar shells that were shot from cannons on the ground. Now, it turns out that if you were going to get killed, the probability of getting killed with flak is 75%, and the probability of getting killed by being shot down was 25%. So, as a rational pilot, what should you always do before you get on that bomber? What should you wear? You couldn't wear both, because in those days it was too heavy to wear a parachute as well as a flak jacket. A flak jacket was a canvas vest that had metal linings, metal plates sewn into the lining. So what would you do? 75% chance of getting killed by flak, 20% getting killed by anti-aircraft fire. Always wear the flak jacket. Well, before these pilots got on, the U.S. Air Force put 2 tables, one with parachutes and one with flak jackets. And they let the pilots choose, because these were all volunteer missions. They were viewed as very dangerous, and the Air Force did not want to force these pilots to go on these missions. Well, what happened is that the pilots picked the parachute 25% of the time, and they picked the flak jacket 75% of the time. And so the Air Force was very disturbed about it, and actually at one point forced all of these pilots to wear only flak jackets, and they absolutely revolted. They complained bitterly, and they said, listen, this is our lives we're putting on the line. You have no business telling us what we can or cannot wear. And so that's when the Army, the Air Force apparently contacted the psychologist, Tversky, to figure out what the heck's going on. So we all do this. They absolutely knew the numbers. Yes, it was communicated to them. And not only did they know the numbers, they saw directly their colleagues getting killed far more frequently by flak than by getting shot down. In those days, it was too heavy. That was it. But now you can do both. But the question is, how stupid could they be to do this? And so when Tom Brennan and I started looking at this question, we said, look, we realize that people can be irrational from time to time. But something so systematic can't possibly just be a matter of stupidity. There has to be another reason for it. And so what we've done in a series of papers, some of which have been published, some of which are still ongoing, you can take a look at the published ones on our website, is we've developed an explanation for this kind of behavior. A very, very simple evolutionary model that I'm going to be able to describe to you in approximately 3 minutes. It'll take maybe another 7 minutes to work out the implications using nothing more than high school algebra that actually can explain this and many other kinds of behavior purely from the process of natural selection. And what it suggests is that there's a framework you can use to derive all of these behaviors, and it really hinges not upon the behavior itself, but rather upon the environment. In other words, these behaviors don't happen in a vacuum. They emerge over time in response to certain environmental conditions. And so instead of focusing on the behaviors, what we really ought to be doing is focusing on the environment. And in particular, what we're going to show is that these behavioral biases exist for a reason, and that it really has to do, in fact, with the nature of the risk in the environment, the threat to survival, and whether or not that risk is systematic or idiosyncratic. Now, I'm using phrases borrowed from finance. Systematic risk and idiosyncratic risk we've learned from Bill Sharp's CAP-M. Systematic risk is risk that we are all faced with and we cannot diversify. Idiosyncratic risk is risk unique to us individuals that we can easily diversify. And so it turns out that this notion of diversifiable risk in a population biology context can actually explain a lot of the anomalies that we seem to be struggling with. And not only that, but what you get for free almost is a definition of intelligence, of bounded rationality, of where that bound is defined according to environmental threats and resources from the biological perspective. And it provides a basis for what I've been calling the adaptive markets hypothesis, the alternative to efficient markets that Fama and Samuelson pioneered. In fact, this year's Nobel Prizes, I think, really underscore that kind of a dichotomy between behavior and efficiency. The fact that Fama and Schiller got it the same year, I think, was an inspired choice by the Nobel Prize Committee. And the fact that they gave it a Hansen as well suggests that there's a quantitative perspective that you can take to reconcile behavior with efficiency. So I'm going to try to do that. Exactly. And it's perfectly reasonable to do so. Now, there's a long literature for this. I won't have time to describe since time is short, so you can take a look at the papers. We cite all of the various different literatures that we touch upon, but the idea, you'll see very, very quickly, is a very simple framework. So let me start with the framework. It's a simple binary choice model where creatures in our setting choose between two things, A versus B. And to make it simple, we're going to consider creatures that are asexual semiparous individuals. By asexual semiparous, I'm not referring to MIT undergraduates. Someone said that they thought that's what MIT students were like. What I mean by that is creatures that reproduce without sexual interaction. They just reproduce by giving birth, and they do this once in their lives. Semiparous means they give birth once and then they die. Now, they make one decision in their lifetimes, and that's to choose between two things, A versus B. It doesn't matter what those things are. All that matters is that if you choose A, you will get one set of offspring, XA, which is a random variable. And if you choose B, you'll get another set of offspring, X of B, which is a different random variable. And so really the joint distribution of these two random variables describes the entire biology and environmental conditions of this very, very simple setting. Okay? And behavior is going to be modeled as simply how you choose A versus B, and the genetics of this problem is captured by the assumption that the offspring will behave identically to the parents. So in this case, there's no mutation, there's no crossover, there's no complex kind of reproductive dynamics. It's literally children behave identical to the parents. So it's a very stylized model of reproduction. But very quickly, you'll see why it is we're doing it and how we can easily generalize this. So we start off with an individual that I'm going to parameterize by a single number f. F is the probability that this individual will pick A versus B. So you can think of the behavior as a simple coin toss where the individual has a probability of choosing A versus B with this parameter f. So f describes this individual's behavior. And by the notion that the offspring behaves exactly like the parent, what I mean by that is that if you start out with a particular f, your children will be the same f, and their children will be the same f, and so on and so forth. Okay? And you don't get to pick anything. You're simply born a particular f. So if your f is 0.5, that means that you will flip a fair coin, and with probability 0.5, you'll pick A. With probability 0.5, you'll pick B. And your children will also be 0.5 Fs. If, on the other hand, you're the type that always picks A, then that means F is equal to 1 for you, and your children will always pick A, F equal 1 for them, and so on. F can be anything between 0 and 1, including 0 or 1. And so the nature of behavior in this very, very simple setting is a combination of random choice or deterministic choice, depending on whether F is strictly between 0 or 1 or at the endpoints. So the idea behind this, whoops, seems to be stuck. Here we go. I'm going to start off with a uniform population on 0, 1. So I'm going to start off with every possible type of F with equal numbers in the beginning of my ecology. And I'm going to let them reproduce, given a joint distribution for XA and XB. And I'll let them reproduce over many, many generations. And over time, I'm going to see whether or not there's a particular value of F that becomes overrepresented. And if there is a value of F that is overrepresented, in this case, F sub 4, then that's the behavior that emerges from this primordial soup of completely uniform behaviors. That's the sense in which behavior is going to be said to evolve in this context. Okay? We start with a very simple binary choice problem that all of these mindless individuals begin picking with particular probabilities, and their offspring pick the same probabilities and so on. And over time, we're simply going to see which of the Fs becomes overrepresented. Now, I need to make some assumptions in order to derive some results. So I'm going to assume first that the joint distribution of XA, XB is identical across individuals. That means that if you pick A and I pick A, we're going to both get the same number of offspring, X sub A. It's the same realization. So it's identically distributed across population. Over time, I'm going to assume that it's IID. It's independently and identically distributed. This corresponds to a situation where we have systematic environmental risk, meaning if you pick A and I pick A, we get the identical outcome. Effectively, we are part of the same ecology, the same environment. Okay? These individuals, let me remind you, are mindless. They don't know that they're a particular F. They just simply exist as a kind of behavior. And the question is, which of these various Fs from 0 to 1 survives over many generations? In other words, what kind of behavior evolves? And the mathematics of it is trivial. We simply find the F star that maximizes the geometric growth rate of that population. Right? You can optimize the growth rate of this population, given this assumption about distributions, maximize F to maximize the growth rate, and that F star will be the behavior that survives. And so it turns out that the mathematics is pretty simple. I won't take your time to do it now, but you can take a look at the paper. The F star that maximizes the geometric growth rate has 3 possible values depending on the relative reproductive success of A versus B. If the expected value of the offspring, if you choose A, divided by the offspring, if you choose B, if that expectation is greater than 0, and the expectation of the reciprocal is greater than 1, and the expectation of the reciprocal is less than 1, you should always pick A. F star is equal to 1. If the expectation of xa over xb is less than 1 and the expectation of the reciprocal is greater than 1, you should always pick 0, always pick b. But if the expectation of xa over xb is greater than or equal to 1 and the reciprocal is also greater than or equal to 1, then it turns out that you should randomize. And the randomization is the implicit solution to this equation right here, which looks a lot like one of these Euler equations. But what it says is that you should randomize between A versus B in order to equalize the expected offspring across the two, the expected reproductive rate across the two possibilities. Now, let me give you some intuition for this. But do it by way of a simple numerical example. This just basically says that the f star grows exponentially fast relative to any other f. So f is the f star, it takes over. So let me give you a simple example to illustrate how this works. Suppose that the joint distribution of xa and xb is also a Bernoulli example. There are two states of the world, either state 1 or state 2. In state 1, if you pick A, you get M offspring. If you pick B, you get 0 offspring. In state of the world 2, if you pick A, you get 0 offspring, or you get M offspring if you pick B. And the probability of state 1 versus state 2 is P, or 1 minus P. If this is your setting for the joint distribution of XA and XB, when you do the optimization, it turns out that the behavior that maximizes the growth rate is F star equal to P, probability matching. Now, if you're like me, when you look at this doesn't make much sense. So let me give you a biological example. It's a rather artificial example, but one that I think will get the point across. Suppose that you're living in a particular environment where there are two states of the world. Either it's rainy or it's sunny. And as a creature in this environment, you've got one decision to make, which is where do you build your nest? Do you build your nest in the valley or on the plateau? Well, it depends. If you build your nest in the valley, then there's plenty of water in the valley. There's a stream that runs through it. And because you're in the valley, in case there's sun, the rays of the sun are shielded by the shadow of the valley. And so that's a good environment where you've got 3 offspring if you pick A and it's sunny. However, if you build your nest in the valley and it rains, the river floods and your offspring will drown, in which case there are no survivors and your offspring are all killed. Okay? If, on the other hand, you build your nest on top of a plateau and it's sunny, well, that's bad news because the sun will burn your offspring to death. There's no water, and so you will either die of thirst or of exposure. But if it rains and you're on the plateau, you won't drown because it's a plateau, the water drains, and there's plenty of water, and the clouds will protect you from the rays of the sun, so your offspring will survive. So let's suppose that the probability of sunshine is 75% and the probability of rain is 25%. As an optimizing economist, where would you want to build your nest? Always, always in the valley, right? Because that maximizes the expected number of offspring you're going to have. You're always going to build your nest in the valley because it'll always have the highest probability of allowing your offspring to survive. Well, suppose you do that. Let's simulate this very, very simple environment. Let's simulate it with a few different behaviors. Behaviors where you randomize building your nest in the valley or on the plateau at 0.2, 0.5, 0.75, which is the probability of sunshine, or the economist here, f equal 1. F equal 1 means you always build your nest in the valley. Let's see what happens. Well, we start the simulation. It turns out that the economists are growing faster, faster, and the fastest of all. Oops. Until when? Until the first time it rains, all the economists are wiped out, which may be a good thing from the INET perspective. The first time that it rains, all of the economists are killed, and therefore their offspring are no more. Therefore, that behavior, the behavior of always picking the valley, that behavior can't survive. It's not sustainable because if we are all doing the same thing, and we are all subject to the same environmental risk, The first time that environmental risk goes bad, we're all wiped out. Nature likes a diversified bet. And so it turns out that the population that grows the fastest is actually the one that matches the probability of this particular environmental threat. Because by matching the probability, you are equalizing the expected survivors in no matter what the state of the world is. That's what probability matching does for you. It's not rational from the individual perspective. It is true that from the individual economist perspective, we are still maximizing our own personal expected number of offspring by acting selfishly. But by acting selfishly, we don't allow our species to persist. We don't allow this behavior to persist if we are all engaged in the same environmental exposure. So this is an example where because the environment has systematic risk, we have to exhibit very idiosyncratic behavior. We have to diversify our behavior. It's not that any one of us decides we're going to do it. It's simply that the behavior that happens to be the most diversified ends up being the one that has survived. Now, since I'm running out of time, I won't describe to you the general result. We have a more general case where we can show that there are all different kinds of behaviors that are possible depending on the environmental threat. And it's only a very narrow case, this equation, this line here, where probability matching exactly emerges. All other environments that are different points on this graph illustrates different behaviors that emerge. There's a rich set of behaviors that are optimal from the environmental perspective as the environment changes. So the last thing I want to describe before summarizing is that there are many different behaviors that we can get out of this using a very simple set of parameterizations. Probability matching, randomization, risk aversion, risk-sensitive foraging, loss aversion, anchoring, framing, many of the things that the psychologists have said are totally irrational and stupid, it turns out that there are environmental explanations for that. But it turns out that these results hinge on a very critical assumption. And if you change that one assumption, all the results go away. And you know what that one assumption is? The assumption that we are all facing systematic risk. If I change one very simple assumption, instead of assuming that this joint distribution is identical across all of us, if I simply made it independently and identically distributed across all of us. In other words, if you pick A and I pick A, you will get XA, and I will get XA, but those two XAs are actually independent realizations using the same distribution. So that means that your XA could be 3 offspring, my XA could be 8 offspring, even in the same generation. It's as if we're all living in our own little tiny microclimates, so that it's sunny for you, but it's rainy for me. In that case, if we do the exact same simulation, but we make that one assumption, then it turns out that the law of large numbers applies in a very different way, and what we get when we run the simulation is what we exactly expect, which is now, all of a sudden, the economists are the ones that are going to survive. Because the probability that it rains on all of the economists at the same time is 0, given that the distribution is idiosyncratic across the economists. So, to summarize, our perspective is that there are lots of different extensions that can use this framework to derive behaviors that people have thought were either irrational or nonsensical. And this kind of an approach actually gives you a mathematical foundation for intelligence as well as bounds on intelligence. We can build in mutation, so you can get sexual reproduction. We've incorporated learning. We've also incorporated strategic behavior. That's key. So far, in this setting, I've assumed nothing about strategic behavior. And the reason that that's the case is because there are no resource constraints. I can pick A and B and get XA and XB irrespective of what happens to you. But if my choice ends up impinging on your possibilities, then all of a sudden, we now have strategic behavior that will emerge as well. And lastly, group selection and punctuated equilibrium, things that evolutionary biologists have been arguing about and have discussed in a variety of contexts, we can actually derive that in our setting and provide a nice resolution. So let me conclude by saying that this is a framework for modeling the evolution of behavior that really abstracts from the underlying genetics. The biologists are absolutely keen on focusing on the genetic basis. We simply assume there's a distribution phi of XA and XB, and for us, the biological reduced form is just fine. The simplicity of the probability matching case tells us that that is likely to be a very primitive behavior that's hardwired in all of us. But there are many other behaviors that really come about because of the underlying environment that we live in. Economists have a very fond saying to politicians. They'll say, it's the economy, stupid. But I actually think that we ought to be telling the economists, it's the environment, stupid. It's all about the environment. That's what ultimately dictates how behavior evolves. Thank you.
Thank you for keeping us time. So
you know the book of Rolf Meister. Is there anything good about man? So he's a professor of anthropology, and he very interesting question of why do we take risks? Very big. And just wanted to make a paper which was very strongly along the lines in Journal of Theoretical Biology, where we arrive exactly according to the same philosophy of the population, selecting very bizarre behavioral models of decisions that actually promote risk in man versus.
Yeah.
So that's something that I just want to connect. But I wanted to ask you a question very quickly.
Yeah.
But why? So you show that there's a relatively narrow domain in which this condition holds. Given the fact that there's hammered on us that everybody, all primates, all animals should be probably matching, what on earth gave the fact that the environment is forcing this very word narrow in the space of
well, that's right. So that's a great question. First of all, please send me that paper from the Journal of Theoretical Biology because I want to make sure we properly cite it and relate it. So the reason that probability matching per se seems to be so universal is because it is a very, very narrow set, but it turns out that that narrow set happens to be a very important one from an environmental perspective. That set happens to be the situation where if you have two possible states of the world, then the implications of your choice of A versus B is negatively correlated between those two states. So in other words, the two states you can think of as environmental extremes. If I pick A in one environment, it's really good. But if I just change the environment to something else, it's really bad. If that happens to your choices, then probability matching is the actual right answer.
In a way, I do understand you're saying that you need somehow an argument in which the environment.
You need the argument, two things. One is you need the argument where the environment changes, and secondly, you need the outcome of your behavior to be very good in one state and very bad in the other. If it's good in one state and so-so in the next one, you won't get probability matching. Probability matching comes about only when it's a very, very different outcome in the two different states of the world. And actually, the way you can think about it is that this is Mother Nature's way of dealing with tail risk. It is actually a tail risk strategy.
To capture it in your model, because you don't have it.
We do. It's in. So the way that we enlarge it is to say the outcome of A versus B in the two states is arbitrary. And then we say, for all possible arbitrary combinations, what is the optimal strategy? Yeah, that's right.
Yeah, I want to tell about personal experience that is related to what you say and that may happen. And it's a story where I was in a conference, conference room, but like this one, with a guy talking about behavioral finance, and he was making experiments with the. He was making the audience do bets and invest games like this. And I'm a mathematician. I was surrounded with two friends of mine who were both traders. And when he was about to make bets, I did my probability calculations. made a decision which was exactly, this probability matching. So that's stupid. So, I mean, even though I know I did that, and it was probability matching, and something inside me, was like preventing me from being completely black. Whereas the two traders
Yeah.
were laughing at me and say, no, okay, you have to go black or white. Don't do it in between. You're suboptimal. And, it was, we really, were playing, and they were, and so and now, if I put myself in the position of the bank, and I see that those people who are in the market every day have this character of, if they see it, they will go completely black or white in the...
Yeah.
And now, if I may understand that on the level, as you say, of an individual trader. Now, at the level of the bank, according to what you say, I should manage to put something in place so that those traders who have the experience, who are people, if I put me on the trading desk, I'm not very good at that. Now, so those people are way better, but in some sense, how the bank can, avoid the systemic risk that you were describing is knowing that those individuals are people who will have this tendency of doing black.
Right. Exactly. I think that by looking at the population of traders as well as the environment in which they are interacting and seeing which ones survive, you can actually show that there are certain biases that will emerge. One bias that I did not have time to talk about is a very important one from the trader perspective, which I suspect is what you were doing in the experiment, and that's loss aversion. Loss aversion is the phenomenon documented by Kahneman and Tversky and what Daniel Kahneman won the Nobel Prize for. It's a behavior where you are very risk averse when it comes to gains, but you're very risk seeking when it comes to losses. It turns out that we can derive that out of this very simple framework. And that kind of framework makes sense if what you care about is this kind of long-term survival, but it's very bad if what you care about is maximizing the geometric growth rate of your wealth. So from an investment bank's perspective, you absolutely do not want them to be loss averse. But from a human population perspective, we can't help but be loss averse. And that's sort of the kind of biological dynamic that this framework allows you to observe, once you actually put down, what the environment looks like. So that's a great point.
In that case, you have these traders who are all going black, and because they studied elementary.
Yeah.
What happened, at least in one trading room that I looked at, was the guy who ran the room, because you're interested in survival.
Yes.
Actually traded it.
Yep.
These little rational traders who were all on
Right.
to prevent the flood down in the room.
That's right. Yeah. Yeah, and I think that underscores the point that what is good for an individual is not necessarily good for the population. And of course, what nature does, what evolution does, is it maximizes the population's survival, not the individual's. And so economists, far too often, we focus on what's good for the individual. And that's important. Deriving the rational expectations equilibrium is a useful thing, as long as we understand its limits, particularly when put into the context of the population.
An analogy, which my answer is quite clear, but I'm not sure that I follow it very clearly, because it looks like there's an example of evolution. You have
Yes.
essentially the fact that you have to follow a certain fixed reality
Yeah.
to have the optimal fraction.
Yes.
Whereas if the realization is independent for all the different individuals, then essentially you are making a summary.
Right.
And the whole thing, so I want to have in addition to this, it's very, very similar.
Yes.
I mean, I didn't know about,
Yeah.
it sounded
Yeah. Absolutely. So let me comment on two of those, because those are both very good points. So I'll talk about the second one first. The Kelly criterion, for those of you who don't know it, is where you maximize basically log utility. You're maximizing geometric growth rate of your wealth. This is similar in the sense that what nature does is maximize the geometric growth rate of your population. I mean, that's what natural selection does. But there's a connection between the Kelly criterion and this model. This model actually will give you the utility function that will emerge. and it turns out that the utility function that emerges under relatively weak conditions is not log utility. Log utility emerges as the selfish thing to do for maximizing your own wealth. It turns out that that utility can't persist if you have lots of different kinds of utility over time and an environment that is both idiosyncratic and systematic. But the reason it looks similar is not an accident. It's because the population arithmetic relies on maximizing geometric growth rates, which is what Kelly does. Yeah. Your first question about stationarity, or rather ergodicity. So we use the law of large numbers and even the central limit theorem here, but we apply them in very specific ways, both the cross-section of the population as well as over time. If you don't have stationarity and ergodicity, which I would argue in the real world we don't have that, then what you get is behaviors that shift over time. You get risk aversion that increases or decreases. You get probability matching that gets worse or better. So you get behaviors that vary through time and conditions. But that's what we see in the real world. So once again, instead of trying to uncover the deep parameters that rational expectations economists focus on, forget the deep parameters, focus on the environment, and ask the question, in this particular environment, what are the evolutionarily growth optimal behaviors? That, I think, will allow you to give a very different perspective than the typical stationarity and ergodicity assumptions that we take for granted. Point well taken.
Okay, so I think
Can your theory speak to altruism? A long time ago, I worked at a couple of levels of biological systems. First of all, animal behavior, and then, at molecular level, essentially, genetic style. And there's evidence there that evolution has actually built in some altruism. And we know there are different kinds of individuals, like the black and white.
Yes. Yes.
So does
it absolutely does, and I think it speaks to it in a way that's even more primitive than how evolutionary biologists have spoken to it. So first of all, William Hamilton was the first to argue that altruism emerges naturally from evolution. And he had a very simple model that was actually extended by Robert Trivers, where basically you can show that because you share more genetic material with your brother or sister, you would actually prefer to save them than your cousins or your distant relatives. But that's a very complex genetic explanation. We have a very simple explanation of altruism here. In fact, I just showed you altruism. Altruism is, I'm not going to do the self thing and maximize my own offspring. I'm going to do what will allow my type to survive. Now, in this case, it's totally mindless. But the fact is that what looks to us like altruism is really simply nature selecting for the most robust kind of behavior. And with more complicated environments, I can actually induce even more remarkable feats of altruism than this. And there's nothing mysterious about it. It's really just a stochastic environment interacting with natural selection.
Hans Clare in Zurich has developed a series of experiments on altruistic diminishment and all these paradoxes. And indeed, the class of problems exactly on this time can actually see the derivation, the evolution potency of this trade-off. Altruism directly from the as a collective behavior, even if it's not rational.